This is One-on-One. We have Dr. Bryan Pfister, who is Associate Professor, Department of Biomedical Engineering at NJIT. Good to see you, Doctor.
Pleasure to be here.
Now, break this down. Sometimes we have scientists here. We're like, what are you talking about? But you are talking about stretching axons, the part of the nerve cell that sends electrical impulses. Talk to us, and why have you brought silly putty to break this down? Go ahead, talk to us.
Okay, so what my area of research is in traumatic brain injury. That's where we're looking at how the brain gets damaged to some sort of physical insult. The axons are these wires, as you had mentioned, that connect all the different neurons in the brain that send the signals around the brain. And in many brain injuries, we lose those wires, then we lose the signal. The reason I brought the silly putty is to give you an example of how the different types of injuries might lead to different types of brain injuries. So for example, if you're in an automobile accident, you might expect to be in a different situation than if you were playing football, or if you were in a war and got exposed to some sort of blast wave.
So the type of brain injury matters a great deal with respect to what?
To the physical insult, the traumatic event that occurs. And if I may,
sure.
I brought a little childhood toy here called Silly Putty.
Got it.
Right? This is what we call a viscoelastic material. Which viscoelastic material.
Got it.
Visco meaning it's a little bit of fluid, it flows. Elastic meaning it has some structure to it, so it's a solid. And the key is that the rate at which you work with it, or how fast you apply your forces, determines on how the material behaves. So if I stretch it slow, right, it stretches. If I pull it fast, it breaks, right?
Got it.
And then if I even go to a much, much larger rate, so you can think about something that might get towards closer to a blast, it bounces, right? So it bounces and it doesn't deform. So the rate at which you apply the forces to the material determine on how it behaves.
Now, were they supposed to replicate certain kinds of injuries?
Absolutely. So the idea is now you start thinking about brain as being something more like Jell-O than silly putty, right?
Right.
So if you deform it slow, if I took silly putty and shook it on a plate.
Give me silly putty back, guys. This is a brain. Don't be throwing around like that.
Exactly. So now if we look at something like Jell-O, if we shake it on a plate, it wiggles, right? And if we look at something, a brain's going to be a little bit more like Jell-O-like than silly putty-like.
Not as elastic.
Not as elastic. Well, actually, softer in a sense, right? Because it's more squishy. But in a very similar rate, at much higher rates, if I was to expose Jell-O to extremely high rates of force, then it would start behaving more solid-like the silly putty did when I dropped it on the floor. I stretch it slow, it deforms. I drop it on the ground, it bounces, and it does not deform. In fact, if you took silly putty and shot a gun at it, it would actually shatter into a bunch of little pieces. So it's the rate at which you deliver the forces.
But Doctor, ultimately, in layperson's language, when it really comes down to people who are watching right now saying, okay, this is fascinating.
Yeah.
What does it mean in terms of the treatment of these injuries?
Well, what we're thinking is that the different forces can lead to different types of brain injuries. So if you're in an automobile accident, it would be a much slower force application to the head than if you were in a blast wave, right? So the blast is extremely fast. A blast wave happens on the order of microseconds, where a automobile accident, your brain goes through forces that occur over several milliseconds, several hundred milliseconds, in fact. So what happens is we're finding that the different types of insults to the head are leading to different types of brain injuries. So in an automobile accident, a lot of people can come out with very severe injuries, very slow injury, a lot of deformation of the brain tissue, a lot of damage occurring. In a blast wave, we don't really see that injury as much. We can't image it. We can't.
So on the MRI, doesn't it show up?
It's not on the MRI.
It's not on the MRI.
No, it is not.
So what do they look the same?
These axons are microscopic, right? These connections are microscopic.
You can't see them in the MRI.
Exactly.
So Muhammad Ali boxing or others who are boxing are getting multiple, hits to the brain. Something's happening to the brain, right?
Right.
Football player, multiple concussions. Something's happening to the brain.
They can't image it.
They can't image it.
So they're going off of symptoms when someone comes in. So the biggest problem we have now, 1.7 million Americans have a brain injury each year. right? There's a huge percentage of them that are mild. Some that might not even go to the hospital because they don't recognize until weeks, months later. They can't remember things, they're angry, they're not getting along with their wife, they're having a tough time at their job.
But your research potentially could do what?
What we're trying to do is we're trying to understand what is happening at that microscopic scale. So since we can't image it, we try to understand what is happening to the nervous system under these different types of physical forces that replicate the brain injury, to try to understand what's happening to the nervous system. If we understand what's happening to the nervous system as a result of the damaging forces, that gives us what we call targets that we can try to mend, right? So if we don't know what we want to fix, then it's hard to pick a treatment strategy to try to fix or cure the problem.
You know, as I'm listening to you, doctor, I'm realizing you're talking about the scientific process, which is slow by layperson's interpretation like mine, which is methodical, which it needs to be, which has to have all these controls. And I'm sitting there going, yeah, and so what's the solution? It doesn't work that way.
Correct. It does not.
By design.
By design, right. So if, you know, when a doctor wants to come in and say, okay, you have a brain injury or you have something wrong with you, you have diabetes. Okay, well, if you have diabetes, I know that we need to look at an insulin issue.
Here's the protocol.
A target. That's a target. We know what we're going to happen. We know what the problem is.
Brain injury is different.
We don't know what the problem is. We don't know how to fix it. So how do you pick a treatment?
We're way behind on this.
Correct. So you have to understand what the problem is first.
This is fascinating work. With 1 minute left, why is this your field of research?
That's actually
in 1 minute or less.
One long and or less. I actually worked with some colleagues that approached me one time and said, do you know what this term is? And they said DAI. It stands for diffuse axonal injury. And it's this mechanical damaging of the nervous system that leads to all this what's going on. And I was a mechanical engineer wanting to get into biomedical sciences.
Were you hooked?
And I was hooked from that moment.
Well, you and your colleagues at NJIT are doing groundbreaking work.
Thank you.
Every time we have one of your colleagues on, we learn something new. Dr. Bryan Pfister, Associate Professor, Department of Biomedical Engineering at NJIT. We appreciate you teaching us, and I'll try to be more patient. Thank you very much.
Thank you.
One-on-One with Steve Adubato has been a production of the Caucus Educational Corporation, celebrating 25 years of broadcast excellence. Funding for this edition of One-on-One with Steve Adubato has been provided by Fedway Associates, Inc., the Russell Berry Foundation, Cone Resnick, New Jersey Natural Gas, Verizon Communications, and by the law firm of Gibbons PC. Promotional support provided by the Star Ledger and NJ.com. Transportation provided by Airbrook Limousine. One-on-One with Steve Adubato has been produced in partnership with St. Joseph's Healthcare System.